Dear students, in the last class I gave two homework. First we discuss the answer of these questions. The first question is, write down the sequence of natural numbers ending in 1 or 6 and describe it in two other ways. I hope that all of you got the answer. Let's discuss the answer. First we write the natural numbers ending in 1 or 6. They are 1, 6, 11, 16, 21, 26, etc. These are the natural numbers ending in 1 or 6. Describe this sequence in two other ways. One method is given, the sequence of natural numbers ending in 1 or 6. Describe in two other ways. First we find the characteristic or peculiarity of these numbers. We know that these all numbers leaves remainder 1 when it is divided by 5. It is clear that when the first number 1 is divided by 5, the quotient is 0, the remainder is 1. The second number 6, this 6 divided by 5, 1 times 5, remainder 1. Third number 11, 11 divided by 5, 2 times 5 2s are 10, remainder 1. Similarly, we can check in the remaining terms also. That is, all the terms satisfies this property. What is the property? They leave remainder 1. They leave remainder 1 on division by 5. That is the second method. That is the first answer. Sequence of numbers leaves remainder 1 on division by 5. It is the one method. Then we find another method. What is the peculiarity of this number? Another peculiarity of this number. Similarly, we divide by 10. That is the first number 1 divided by 10. We got quotient 0, remainder 1. Second number 6 divided by 10. Again quotient 0, remainder 6. Third number 11 divided by 10. Quotient 1, remainder 1. Next number 16 divided by 10, quotient 1, remainder 6. Now we got the remainders are either 1 or 6. There are two remainders, either 1 or 6. So we list the numbers as, with the property, the numbers or sequence of numbers which leaves remainder 1 or 6 on division by 10. That is the second property. Sequence of numbers leaves remainder 1 or 6 on division by 10. These are two different methods to express the given sequence. The dots are arranged in the form of triangle. How many dots are needed to make next two triangles? Answer. Number of dots 3, 6, 10, etc. That is, the number of dots in first triangle is 3. dots in second triangle is 6, dots in third triangle is 10. We have to find how many dots are needed to make next two triangles. That is, what are the next two terms of the sequence. In this, 3 can be expressed as 1 plus 2. That is sum of first two natural numbers. 6 can be written as sum of first three natural numbers. 10 can be written as sum of first four natural numbers. Similarly, next term is sum of first 5 natural numbers, that is 15. And next term is sum of first 6 natural numbers, that is 21. Therefore, the dots needed to make next two triangles are 15 and 21. Consider the next question. Make the following number sequence from the sequence of equilateral triangles, squares, regular pentagons, and so on of regular polygons. First one, number of sides, sum of interior angles, sum of outer angles, one interior angle, one outer angle. First we find the number sequence of number of sides. Here the regular polygons are, first one equilateral triangle, next square, third one pentagon, hexagon, and so on. We know that triangle have 3 sides, square have 4 sides, and pentagon have 5 sides. So the side sequence of sides is 3, square 4 sides, pentagon 5 sides, etc. That is 3, 4, 5, etc. Sum of interior angles. We know that sum of interior angles of a triangle is equal to 180. Square, that's equal to 360. Pentagon, that is 540. It is already studied in 9th standard. Therefore, sequence of sum of interior angles is 180, 360, 540, etc. Sum of outer angles. We know that the sum of outer angles of regular polygon is 360 degree. Therefore, sequence of sum of outer angles is, in triangle it is 360 degree, in square it is 360 degree, in pentagon also it is 360 degree. That is, in any regular polygon, the sum of exterior or outer angle is 360 degree. Therefore, the sequence is 360, 360, 360, etc. Next, the sequence of one interior angles. We know that the sum of interior angles of triangle is 180 degree, square is 360 degree, pentagon is 540 degree. Triangle have 3 sides, therefore one interior angle is 180 divided by 3, that is 60 degree. Square have 4 sides, so one interior angle is 360 divided by 4, that is 90 degree. Pentagon have 5 sides, then 540 divided by 5, that is 108 degree. Therefore, sequence of interior angles is 60, 90, 108, etc. And the last question, sequence of one outer angle. One outer angle. We know that the sum of outer angle of any regular polygon is 360 degree. In the case of triangle, there are three outer angles, then one outer angle is 360 divided by 3, that is 120. In square, there are four outer angles, 360 divided by 4, that is 90. In pentagon, there are five outer angles, that is 360 divided by 5, 7 5s are 35, 2, 72. Therefore, sequence of outer angles is 120, 90, 72, etc. Next, algebra of sequences. We know that the terms of the sequence are denoted as first term x1, second term x2, third term x3, etc. Then the last term or nth term is denoted by xn. This xn is called algebra of the sequence. Algebra of the sequence means how these terms of the sequence are related to natural number. There is a relation between the natural number and terms of the sequences. This relation is called algebra of the sequence, and this is denoted by xn. Consider some questions. Write the algebraic expression of sequence of odd natural numbers. We know that the sequence of odd natural numbers are 1, 3, 5, 7, etc. We have to find out the relation between natural numbers and these terms. We know that 1, 3, 5, 7 are very close to the even numbers 2, 4, 6, 8, etc. That is 2 minus 1, that's equal to 1. 4 minus 1, that's equal to 3. 6 minus 1, that is 5. 8 minus 1, that is 7. These are odd natural numbers. Even natural numbers can be written as 2n, 2 into something, 2 into n. Minus 1 means 2n minus 1. If we put n equal to 1, we got the first term. N equal to 2, we got second term. N equal to 3 got third term, n equal to 4 got fourth term. So, algebraic expression is n minus 1. Next one. Write the algebraic expression of sequence of natural numbers which leave remainder 1 on division by 3. Here, the sequence of numbers are 1, 4, 7, 10, etc. We have to establish a relation between natural numbers and this term. So, 1 is written as 3 minus 2. 4 is written as 6 minus 2. In this way, 7 can be written as 9 minus 2. So, how can we express 10? That is 12 minus 2. Minus 2 is common or fixed. There is change on the part first one, 3, 6, 9, 12. Everybody got the idea? 3, 6, 9, 12 are multiples of 3. Any multiple of 3 can be written as 3n with minus 2. So, algebraic expression is 3n minus 2. Write the algebraic expression of sequence of natural numbers ending in 1. The sequence of numbers are 1, 11, 21, 31, etc. Here also find the relation between natural numbers and these terms. How 1 is related to 1, how 2 is related to 11, 3 related to 21, 4 related to 31, and so on. So, this 1 can be expressed as 10 minus 9. 11 can be expressed as 20 minus 9. 21 can be expressed as 30 minus 9. So, the next term that is 31. Clearly you say that 40 minus 9. Here minus 9 is fixed. Change on the first part, that is 10, 20, 30, 40, etc. 10, 20, 30, 40, etc. It is clear that a multiple of 10. Any multiple of 10 can be written as 10n with minus 9. So, the algebraic expression is 10n minus 9. Next question. Write the algebraic expression of sequence of natural numbers ending in 1 or 6. We know that the sequence of numbers ending in 1 or 6 are 1, 6, 11, 16, etc. What is the question? Write the algebraic expression or general form. As we do earlier, we have to find relation between natural number and these terms. We know that natural numbers are 1, 2, 3, etc. These natural numbers are how to relate it to these terms. So, we first of all express these numbers as, that is 1 equal to 5 minus 4, 5 minus 4 equal to 1. Next 6 equal to 10 minus 4, 10 minus 4. Now you got the idea, 5, 10, 5, 10. Then next number 15. That is 11 equal to 15 minus 4. Then what's the next? 5, 10, 15, 5, 10, 15. What's the next? 20. That is 16 equal to 20 minus 4. Now we got the idea. 5, 10, 15, 20, 25, etc. are multiples of 5. Any multiple of 5 is of the form 5n with minus 4. So, algebraic expression is 5n minus 4. We pass to next question. For the regular polygon starting with equilateral triangle, write the algebraic expression for the sequence of sums of interior angles, sums of outer angles, measure of an interior angle and measure of an outer angle. First one, sequence of sums of interior angles. We know that the regular polygons are equilateral triangle, square, regular pentagon, regular hexagon and so on. Also, the sum of interior angles of equilateral triangle is 180 degree, square is 360 degree, regular pentagon is 540 degree. Therefore, the sequence of sums of interior angle 180, 360, 540, etc. This 180 can be written as 1 into 180. So 360 is 2 into 180. 540 is 3 into 180. 1, 2, 3 is natural number. So the relation is 180n. That is algebraic expression is 180n. Next, sequence of sums of outer angles. In 9th standard, we already studied that in a regular polygon, the sums of outer angles is 360 degree. That is, the sums of outer angles of equilateral triangle is 360 degree. Square is 360 degree. Regular pentagon is 360 degree. That is, the sequence of sums of outer angles is 360, 360, 360, etc. Therefore, algebraic expression is 360. That is xn equal to 360. Next, we have to find the sequence of measures of an interior angle. Here the polygon is regular. In regular polygon, each interior angles are equal. Also we know that the sum of interior angles of triangle is 180, that of square is 360 and pentagon is 540. So one interior angle of equilateral triangle is 180 divided by number of sides. Number of sides in triangle is 3. So one interior angle is 180 by 3. In square, 360 divided by number of sides, that is 4. In regular pentagon, 540 divided by number of sides, 5. So, sequence of measures of one interior angle is 180 by 3, 360 by 4, 540 by 5, etc. Algebraic expression means how these terms are related to natural numbers. Here terms are fractions, so there are numerator and denominator. How the numerators are related to natural numbers? Numerators are 180, 360, 540, etc. These all are multiples of 180, that is 180 and what about denominator? Denominators are 2 more than natural numbers, that is n plus 2. If the natural number is n, then 2 more than the natural number. 1 plus 2, 2 plus 2, 3 plus 2, etc. So, the algebraic expression xn equal to 180 by n plus 2. Next, sequence of measure of one outer angle. We know that the sum of outer angles of equilateral triangle is 360, square is 360, regular pentagon is 360. Since it is a regular polygon, each outer angles are equal and each angle equal to 360 divided by number of sides. That is, in equilateral triangle 360 divided by 3, in square 360 divided by 4, in pentagon 360 divided by 5. That is, sequence of measures of one outer angle is 360 by 3, 360 by 4, 360 by 5, etc. Therefore, the algebraic expression is 360 divided by n plus 2. Denominators are 2 more than natural numbers. Therefore, xn equal to 360 divided by n plus 2. We pass to next question. The first picture is got by removing a small triangle formed by joining midpoints of an equilateral triangle. The second picture is got by removing such middle points from each of the red triangles in the first picture. Third picture shows the same thing done on second. How many red triangles are there in each picture? Taking area of original uncut triangle is 1. Compute the area of small triangle in each picture. What is the total area of red triangles in each picture? Write the algebraic expression for these three sequences. I explain the figure. In the first figure, a triangle is cut from the given equilateral triangle by joining the midpoints. So we got 4 equilateral triangles in this. 1, 2, 3 and 4. There are 3 red triangles and 1 cut triangle. 3 red triangles. In the second figure is formed from this first one by joining midpoints of each red triangles. The shaded triangles are red. So we got 3 red triangles and 1 cut triangle, that is total 4 triangles. Here also total 4 triangles, here also total 4 triangles. Among these 4, 3 are red, here also 3 are red, here also 3 are red. So total 9 red triangles here. Then pass to third figure. Again these red triangles, by joining the midpoints, new triangles is formed. So there are 3 red triangles. These 3 red triangles again divided into 4 parts. Among these 3 are red. So the number of red triangles here 3, here 3, here 3, total 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 3s are 27. 27 red triangles are there. Then what is the first question? How many red triangles in each picture? First picture 3 red triangles. In second picture there are 9 red triangles, and in third picture there are 27 red triangles. Therefore, sequence of red triangles is 3, 9, 27, etc. Second question. Taking area of original uncut triangle is 1. Compute the area of small triangle in each picture. So, we find how many triangles in each picture. Here 3 red triangles and 1 uncut triangle. Therefore, total 4 triangles in first figure. 4 triangles. In the second figure, here is 4 triangles. Here is also 4 triangles. Here is also 4 triangles. Then what about cut portion? Here also we contains 4 triangles. We can divide this into 4 parts like this. Divided into equal parts, we got 4 triangles. So 4, 4, 4, 4, 4 fours are 16 triangles. Then what about this one? Here totally 4 triangles. 1, 2, 3 and 4. In this, there are 4 triangles. Here also 4 triangles. Here also 4 triangles. This uncut region is also divided into 4 triangles. Like this. Then how many triangles are there? 16 triangles. 4 times 4 become 4 fours are 16. Then 16 into 4, that is 64. How many triangles are there? 64 triangles. Then what's the question? Taking area of original uncut triangle, that is the area of the bigger triangle is 1. Then compute the area of small triangle in each picture. How many small triangles? 4. Then area of one small triangle in first figure is 1 by 4. The large triangle is divided into 4 equal parts. So the area of one triangle is 1 by 4. Then what is the area of small triangle in second figure? There are total 16 triangles. Then area of one triangle is 1 by 16. What about third question? There are 64 triangles and area of one triangle is 1 by 64. Therefore, sequence of area of small triangle is 1 by 4, 1 by 16, 1 by 64, etc. Next question. What is the total area of red triangles in each picture? In the first picture, there are 4 triangles, 4 equal triangles. Among these, 3 are red. That is, total area of red triangle is 3 by 4. Out of 4, 3 are red. That is 3 by 4. What about second question? There are 9 red triangles and total number of triangles are 16. Out of 16 triangles, 9 are red. So, area of red triangles is total area of red triangles in second figure is 9 by 16. There are total 16 triangles. Among this, 9 are red. So, total area of red triangles are 9 by 16. In third figure, there are 64 triangles in total. Among this, 27 are red. Therefore, area of red triangles is 27 by 64. Area of red triangle is 27 by 60. Therefore, sequence of area of red triangles is 3 by 4, 9 by 16, 27 by 64, etc. We pass to next question. Write the algebraic expression of these 3 sequences. First one, 3, 9, 27, etc. This 3 can be written as 3 raised to 1. 9 is taken as 3 square and 27 can be taken as 3 cube. In general, we can write it as 3 raised to n. So, the algebraic expression of the first sequence xn equal to 3 raised to n. Pass to second one. The terms are 1 by 4, 1 by 16, 1 by 64, etc. 1 by 4 can be written as 1 by 4 all raised to 1. Same way, 1 by 16 can be written as 1 by 4 whole square and 1 by 64 can be written as 1 by 4 whole cube. In general, it is of the form 1 by 4 all raised to n. So, the algebraic expression of the second sequence is 1 by 4 all raised to n. Then we pass to third question. The terms are 3 by 4, 9 by 16, 27 by 64, etc. 3 by 4 can be written as 3 by 4 raised to 1. Same way, 9 by 16 can be written as 3 by 4 whole square. 3 square equal to 9, 4 square equal to 16. 27 by 64 is taken as 3 by 4 whole cube. 3 cube is 27 and 4 cube is 64. In general, 3 by 4 all raised to n. That is, the algebraic form of third sequence is 3 by 4 all raised to